Alright, so today we're going to be basically looking at page 5 in the notes, the packet on gases. That is kinetic theory of gases. So this is an old machine here. I'm going to get these mixed up. Basically, these are representing the different gases in the room. So I took out the big ones. So our assumptions are these for the kinetic theory of gases. Is that the particles themselves are always in constant motion. Even in solids and liquids, are those particles going to be in constant motion? When we look at gases, we expect that the distance between the gases is much bigger than the size of the particles themselves. So that has a little bit of a pull. That means that they're not going to have these attractive or repulsive forces on each other. But if we were to, let's say, put extreme pressure on these gases, squeeze them together, compress them, then that's not going to be actually true. So this idea won't work under extreme senses of pressure. The other thing that brings gas particles together is cooling them down or extremely low temperatures. Then we're not going to see the particles behaving the way we would like them to. So keep that in mind. The particles move rapidly and in constant random motion. They move in straight lines until they collide. That causes them to change direction. They can collide with another particle, or they could collide with the wall. So take a look at that as that happens. This thing looks like it was made in the 70s. So all collisions are perfectly elastic, so keep that in mind as well. So when you're watching these things hit, we're assuming that they're bouncing off without the loss of energy. Even when they hit the wall, they bounce off the wall at a perfect angle to their approach, and they've lost no energy. So keep that in mind. Again, problems do occur if you get the temperature so low that the particles begin to interact with each other, or you get the pressure up so high that they are compressed and forced to interact with each other as well. Excellent. So scientists have determined kind of a standard for temperature and pressure. And this was designed because anybody can make these conditions in a laboratory, especially if that laboratory is built close to sea level. So if we take a look, standard temperature is equal to 0 degrees Celsius, or, since we know how to do the conversion, 273.15 Kelvin. Standard pressure is 101 kilopascals, or 1 atmosphere. So if you build your laboratory at sea level, it should be quite easy to get 1 atmosphere. And 0 degrees Celsius can be made by using ice and water. If we take a look here, this is 760 millimeters of mercury. So let's take a look. What I'm doing here is blowing up a balloon. So let me actually put the other little side thing there so you can see me. So here I have a balloon. Ask yourself what keeps this balloon inflated. Isn't there 14.7 pounds per square inch pushing on the sides of this because of atmospheric pressure. What is keeping this balloon inflated? And some of you guys might say just gas pressure. But what is that gas pressure caused by? And remember, in the little mechanical thing that I showed you guys, the particles were hitting the edge of the walls. Well, that's what's happening here. The particles are hitting the edges of these balloons. The elastic tries to stretch the balloon back to its normal thing. We know that if there's a hole in it, it's going to squeeze all of that out. So the pressure of the gas inside has to be enough to go against the pressure on the outside, 14.7 pounds per square inch, and against the pull of the elasticity of the balloon. So, what keeps the balloon inflated? Particles hitting the walls of the balloon. And we have to keep in mind that there's particles on the outside hitting the balloon and particles on the inside hitting the balloon. So, let's then take a look at the next part. It says, remember how many particles are in a mole? Well, 1 mole of any gas at STP equals 22.4 liters. So let's imagine that my laboratory is at standard temperature and pressure. Oh, it'd be cold in here. This balloon I have here occupies about 2 liters. I made it about the same size as a 2-liter bottle. So we want to figure out how many particles are there. Well, at STP, right? Remember how many particles are equal to 1 mole? 6.02 times 10 to the 23rd particles. And 2 liters. Every 22.4 liters is 1 mole. And every 1 mole is 6.02 times 10 to the 23rd particles. So with our calculator, 2 divided by 22.4 times 6.02 times 10 to the 23rd. That balloon is going to have well, we only have 1 significant digit because I did estimate that pretty hardly. 5 times 10 to the 22nd particles. That's a lot of particles I breathed into that balloon. Well, what happens if I breathe more particles in? Many of you say, hopefully the balloon gets bigger. And that's kind of what we're going to look at here. Let's think of these 4 things when we look at this. So, particles, volume, pressure, and temperature. I am keeping the number of particles the same because I have the balloon tied. If I squeeze on this balloon in every direction, ignoring the heat from my hands and keeping my laboratory at STP, we squeeze it every direction, right? The volume of the balloon goes down. So we know the particles are equal. The volume goes down. What happens to the pressure? At one point, if the pressure is so high inside versus outside, then the balloon is going to pop, right? And all it needs is 1 weak spot. So as we squeeze the volume down, the pressure goes up. Ignoring the heat from my hands going to the balloon, imagine if I had some insulating gloves, we'll say that the temperature stays the same. We can do this exact same thing with a syringe. So if we take a look, if I squeeze the syringe here, pressure goes up. And then if I pull it out, you can see that the pressure goes down. So take a look here. I'm going to pull this out. See the plunger go back in? That's because the pressure out here is higher than in there. So when I pull that out, the plunger goes back in because of that pressure change. With a smaller volume syringe, you can see it shoots in quite fast. We expand it out. Pressure inside the syringe is low. Pressure out here is high. If we take a look, pressure inside now is higher. Watch what happens when I remove my thumb. You hear a pfft. That's all that gas escaping until the pressure inside is equal to the pressure outside of the syringe. So we can say down here, as volume goes down, pressure goes up. We could also say, as pressure goes down, volume goes up. As long as we keep these two things here. We could also say as volume goes up, pressure goes down, and switch it up. That's known as Boyle's Law. Take a second and watch the video labeled below called Boyle's Law. So Boyle's Law is an indirect proportion. As one goes down, the other goes up, or as one goes up, the other goes down. That math can be shown like this. The initial pressure times the initial volume equals the final pressure times the final volume. Or P1 V1 equals P2 V2. Moving on, we have the idea that what if we were to put this balloon into a hot room? Well, does the number of particles change? It's still closed. So that's the same. This balloon has the ability to move back and forth and get bigger and smaller. We call that elasticity. So people might say that if we put this balloon in a hot room, the gas will expand. So that volume will expand or get bigger. Well, eventually the pressure on the inside and outside will have to equalize again once it changes to the size that its new size. Because we have 1 atmosphere out here, 1 atmosphere in the hot room, that wouldn't change. So the pressure would be the same. The temperature, well, as time goes on, the particles inside of this are going to heat up, which means they're going to be hitting the sides of this wall faster, causing it to expand. So temperature is increasing. So as temperature goes up, volume goes up. A lot of times people say heat rises. Heat doesn't rise. It's actually the heated matter that rises because the heated matter expands. As it expands, it becomes less dense. So it goes up. Hot air balloon, right? A hot air balloon expands out that balloon. Now those particles then go out, and the mass of that balloon, that air mass, and that carriage is less than the density, or the density of it is less than the density of the air around it, which causes it to go up. This is a direct proportion. As one goes up, the other does as well. This is known as Charles's Law. You should take a look at the Charles's Law video down below. One more. What happens if I put a Coke into an oven? Well, here's the deal. The Coke, the volume is constant. It's rigid, the can, right? So we have to keep that in mind. For the Coke, it's rigid. So the volume is constant for the Coke. That means that it's not changing. The number of particles in the can, that's going to stay the same because the can's closed. We know that an oven is going to make the temperature increase, which is going to make the particles in there start to move faster. That's going to build up pressure. That's going to cause the pressure to increase. So as temperature goes up, pressure goes up. I was at a party and this kid, Tommy Palmer, he did that. He threw a can of Coke into a fire as we were all sitting around it. He's like, "Look, Jackson, watch this." And then about, minute and a half, 2 minutes later, basically it explodes and gets hot Coke all over, some people burning their faces. Maybe they have some scars, I don't know. But this is known as Gay-Lussac's law, and this again is a direct proportion. As temperature goes up, pressure goes up. As pressure goes up, temperature goes up. As pressure goes down, temperature goes down. If you have one of those spray cans that you clean your computer off with, like the keyboard, you use that for a few seconds, the pressure in that container goes down. That bottle, that container, it gets real cold. Same idea there. Now we can put all of these into what we call the combined gas law. If the temperature doesn't change, we simply take it out of the equation and we have Boyle's law. If the pressure doesn't change, we take it out of the equation and we have Charles's law. If the volume doesn't change, we take it out of the equation and we have Gay-Lussac's law. But that means now we can actually have all of these things start changing and keep track of all of them and solve for one of the variables. One thing I always ask students to do is to pick a variable and solve the equation for it mathematically. So I suggest you pause the video and solve for T2. Pause now. So the first thing you need to do if you're solving for T2 is you got to get it up top. A lot of teachers will tell you to cross multiply. So T2 P1 V1 equal to P2 V2 T1. We can't leave it on the bottom, otherwise we would be solving for 1 over P2. That's why we got to get it on the top. Well, how do we isolate T2 now so that it's alone? Well, we divide both sides by P1 V1. It cancels out over here, and we get T2 equals P2 V2 T1 over P1 V1. So if you did that, that's awesome. That's what we need you to be able to do. All right, so let's see how this works in motion. So it says a sample of gas occupies 150 milliliters at 25 degrees Celsius. What is the volume when the temperature is increased to 50.0 degrees Celsius? It tells you that P and N are constant. So this is our T1, but not really. 273.15 plus 25.
That would be 298.15.
It's 298.2 Kelvin there. This is our T2, but not really. 273.15 plus 50.
The answer is 323.15.
So if we look, it looks like 25 to 50 is actually doubling. But that's not in the absolute scale. So if we look here, that they're not actually doubling in the absolute scale. That's what's important. So pressure is constant, and number of particles is constant. So the particle number. We have a change in temperature from 323.2 Kelvin to 290, I'm sorry, let's switch these. We have a change in temperature from 298.2 Kelvin to 323.2 Kelvin. The volume is at 150 milliliters. So if we go from what we know, the temperature goes up, If the temperature goes up, we know the volume should go up. Well, let's see how much. So we have P1V1 over T1 equals P2V2 over T2. With that being known, we are not using pressure because pressure is constant. They will cancel each other out. If they're the same number, we just drop it over here. Boom, it cancels. We want to solve for V2. So how do we isolate this? Well, we need to multiply both sides by T2. And we get T2 V1 over T1. These cancel, equals V2. So T2 is 323.2. 323.2 times 150 divided by 298.2.
It's about 162.5754.
162.5 milliliters. And it went up. It went from 150 to 162.5. Notice it didn't double like the temperature here doubled, but that's because we weren't in the absolute value group. We weren't in an absolute scale. Let's try another one on page 8. This one looks kind of fun. Well, I should do one that has all three stuff. What will occupy? Unfortunately, it doesn't look like, looks like this one. Nope. That's sad. Looks like this one. Well, it says there's no change in temperature. Yeah. So you guys have it easy to start with. You don't have any where you actually have all three. So let's go back and make sure that this one does. Sorry about that. A little waste of time there. What would be the new volume if 250.0 centimeters cubed of gas at 25 degrees Celsius and 730 millimeters of mercury pressure were changed to standard conditions? Standard pressure is 760 millimeters of mercury, and standard temperature is 0 degrees Celsius. So that's going to be 273.15 Kelvin. That's good. This is going to be 298.2 Kelvin. And this is fine for a volume. This is V1. We are looking for V2. So, temperature 1, 298.2. Temperature 2, 273.15. Temperature went down, 298.2 to 273.15. Pressure went from 730.0 to 760. Pressure went up. Well, if temperature goes up, usually pressure also goes up. So this one's going to be hard to decide what happens here. Let's see, 250 initial. And this is what we need the math for, because we've got two different things happening. The pressure goes up, the volume should be going down. If temperature goes down, volume should be going down. But these two aren't acting like they normally would. So something out of the ordinary is happening here, but it's fine because mathematically it's okay. Because each one is affecting V differently. So P1V1 over T1 equals P2V2 over T2. So let's go ahead and rearrange this to solve for V2 again. That means T2 is going up top and P2 is going down bottom. They will both be canceled out here. So then we just need to take 273.15 times 730 times 250.0. We've got centimeters cubed there. We've got millimeters of mercury here, and we've got Kelvin here. On the bottom, P2. P2 is 760 millimeters of mercury. And T1 is 298.2 Kelvin. Kelvin, millimeters of mercury cancel out, leaving us with centimeters cubed. 273.15 times 730 times 250 divided by 298.2 divided by 760.
It's about 219.9595.
So the volume did go down like we thought to 219.95, which is going to be 220.0 centimeters cubed. And as I said, it went down. So the idea here is for you to complete problem 2 and 3, and then 1 through 5 on page 8. We'll take a look at those tomorrow. If you have any questions, make sure you do go back to the Zoom.